Focus on the audience. If anyone needs a speaker sheet, let me know. All right.
Is this TV not working over here?
No.
I haven't gotten it to work in several weeks.
And no one's thought to tell me so I can, put any techniques to fix.
If the keyword is stop, the answer is yes.
I should have asked last week when I was sitting there, like, this one isn't working.
The keyword is do, I know.
I'm going to send him another reminder. Okay, he's connecting now. Good.
Oh.
Hello, Dr. Zhang.
Hello, how are you?
Good. So you have a mixed audience, some live and online. We're going to start in about 2 minutes.
Yeah,
Okay, good. Thanks for agreeing to speak to our department.
yeah, thanks for the invitation. I'm glad to be here.
Good. So Steve, you can share his slides in a minute.
I'm actually not even on Zoom right now. So, but,
Okay,
YouTube.
let me make sure I can. Okay. You cannot share screen while the other participant is sharing. So I'm not technically in charge of this.
So I made him a co-host. He should be able to share.
Yeah,
Okay. I just wanted to make sure everything was all set.
Yeah, we are here to help.
Thank you. Okay, and just a heads up to everyone, homecoming is on Friday, and I talked to Jane before I made the schedule, that maybe we should have late Thursday afternoon off, and we do. So there is no colloquium next Thursday, and it's okay to be happy about a day off. I know graduate school life can be very stressful, because I was one for a while. Okay, we are at 3 o'clock right now, and we welcome our colloquium speaker, Dr. Ji Jiang, who will be talking to us about AI, which we've had a few AI searches in our department and a whole big group of faculty on campus. And so we're very excited to get know more about this cohort. In particular, Dr. Zhang works some with GeoAI, which is an area of interest to us. So Dr. Zhang is assistant professor in computer science and engineering, computer information science and engineering at University of Florida. He received his PhD in computer science from the University of Minnesota in 2016 and his bachelor's from China in 2010. He also taught at University of Alabama for 5 years, and his lab's mission is to advance AI and machine learning foundations inspired by interdisciplinary applications. So we're going to learn more about his work today, and the title of his presentation is One Size AI Does Not Fit All, A Step Towards GeoAI. So please welcome Dr. Jiang.
Yeah, thank you for the nice introduction. I'm really honored to be here today. Now let me share my screen. Can you all see my slides?
Yes.
Yeah, let me hide this panel. Oops, sorry. Yeah, can you see the full screen now?
Yes.
Okay, yeah, thank you. Yeah, so today my talk will be about one size AI does not fit all, a step towards GeoAI. And this is the outline of my talk. I will start with a brief overview of the field and discuss about my major research theme. And then I will focus on one representative topic in my lab and on terrain-aware spatial machine learning in observation-based flood mapping. And towards the end, I will discuss some future research directions in my lab to explore collaborations. So first, some background information. Over the last decade, artificial intelligence has revolutionized the society in many domains. Like especially the deep learning technology has achieved tremendous success in computer vision, natural language processing, and games. And the success of AI and deep learning is largely driven by the availability of big data, especially large-scale labeled data, training data like ImageNet, and computational hardware like GPUs and smarter models and algorithms. So given the broad success of AI in these CV and NLP domains, there's a growing anticipation of the same level of achievement of AI in science, especially like geoscience domains. And this is driven by a lot of grand societal challenges like national water resource management, agriculture and food security, and coastal hazard monitoring, and the mitigation and adaptation to climate change. So we know AI for geodomain is important. So what is GeoAI? And this is an emerging research area intersecting AI and the geodomains, or GI science. And there are two different ways to solve this emerging area. One is to use existing AI to solve geodomain problems. But another approach which aligns with my research vision is to probe new AI methods motivated by the unique challenges of geodomain problems. And now let me show you a small example. So this is a real-world area imagery collected in a Hurricane Matthew flood in North Carolina 2016. And we can see there's a flooded area in the image. And suppose we want to use a machine learning or AI algorithm to identify the flood locations on this area photo. If you use a traditional AI algorithm or machine learning algorithm, it will consider this as image classification problems. And then it would produce some flood map like this. And we can see it identifies some exposed flood water surface, but miss a lot of other flood areas, especially those areas obscured by tree canopies. And for this result, there's a lot of efforts required in manual post processing. And in contrast, on the right, I will show a terrain-aware machine learning algorithm developed in my lab that include the topography information into the image classification models and algorithms. And then it produced much more complete results, reduce significant effort in post-processing. And GeoAI, this emerging topic has several new forums, like in both computer science and in GI science domains. And I was a co-organizer of deep learning for spatial temporal data in a major conference in data science and machine learning called the KDD this year. So what are the unique challenges of AI in geodomains? And first, we know the space is continuous. And in geodomain problem, we can easily have an area that can have many thousands by many thousands pixels in a rasterized format. But in contrast, today, the AI algorithm or models developed for the computer vision, like photos or videos, are largely for a size of a few hundred by a few hundred pixels. And also in this continuous space, there's a spatial temporal correlations, tidy connections, and heterogeneities. I think for this audience, a lot of people are very expert in this geospatial effect. But these are very new to AI or machine learning people. And also the data comes from multiple spatial, temporal, and spectral resolutions. And there are noise and missing data and gaps. There's a lot of data quality issues. Another major challenge is that the geodomain problem has existing domain physics and constraints. And one example is, like I showed earlier, is the terrain information. It's very important in hydrological applications. And such physical constraints is very important because AI algorithm or machine learning itself is largely data-driven. And basically, it gives you a model, train a model based on whatever data you give it. So it can happen that the model may really perform well on your training data or even on the validation test data, but when you apply the model to more complicated real-world scenario, it does not generalize well. And one potential strategy to mitigate this issue is to incorporate some more generally applicable physical and constraint or domain constraints into AI and machine learning to make it more robust, especially when there's much fewer training data. And the last but not the least challenge is the paucity of ground truth. In geodomain problem, collecting ground truth may involve the field survey, which is very expensive and time consuming. And so how to develop a training algorithm or learning algorithm for AI models with a limited ground truth is a very important question. And because of these unique challenges, AI for spatial and spatial temporal data has been listed as an open research question by the report from National Science Technology Council. So next, I want to make a brief overview about my major research themes. So here are some works I've been doing to address some of these challenges. And first, to address the challenge of spatial correlation and heterogeneity, I have worked on some new spatial machine learning models like spatial decision tree and spatial assembling, and test some of the algorithm in remote sensing images for wetland mapping data set. And here's some brief result. if you use a traditional decision tree, it assumes that samples are identical and independent and identically distributed, also called the IID assumption. So produce a lot of artifacts. If you consider the spatial context in the tree node test, it can produce better result. And this was largely done when I was a PhD in NSF interdisciplinary project. And then I also works on incorporating the domain knowledge or constraint into the machine learning model structure and algorithms, and develop this topography-aware hidden Markov tree model, and later generalize into deep neural network model, and for observation-based flood inundation mapping. And this was collaborated with several federal agencies. And I have shown in the earlier example that incorporating this terrain-aware domain knowledge enhanced the results significantly. And we get some publications in computer science, AI, or data science venues and remote sensing journals as well. And it was funded by the National Science Foundation and some agencies. And I also works on address the paucity of ground truth training labels. And the idea is that we can utilize some lower quality labels from volunteers or some other coarse versions of spatial data set, and then develop some weakly supervised learning that can train the neural network models, but refining the training data, the labels at the same time. And currently we are testing the algorithms with some preliminary results on the National Hydrographic Dataset Refinement applications in collaboration with the USGS Center of Excellence Geospatial Information Science. And we already got some promising results and some publications. And this is funded by the NSF Data Science AI Machine Learning program. We are also looking for other domain programs. So today, due to limited time, I will only focus on the second work. So next, I will formulate this problem and then discuss two approaches. First, some brief background motivations. So we are solving the application of Earth observation-based flood inundation mapping. And this is important in a flood disaster response, where the first responder needs to know where the flood water is to enhance the situational awareness in flood rescue. And also this is important in national water forecasting. Currently, the NOAA National Water Center operates a hyper-resolution national water model, which forecasts the flow of over 2.7 million rivers reaches at the entire continental US. And however, this model is only calibrated and validated at around, based on observations at around 7,000 gauges, very limited spatial coverage. And one potential idea is to explore using Earth observations like satellite images to derive observation-based flood maps. And that can potentially be used to validate the model in certain space and time areas. So these are the motivations. And next, let's see the definition. First, some basic concept. I think for this audience, people are mostly already familiar with this. So we define a spatial data sample or learning sample as a pixel in a raster framework. And the framework may contain several explanatory feature layers. For example, like the spectral bands in remote sensing images, and also a contextual layer like elevation layer, which contain the terrain information and topography. And we also have a class layer we hope to predict by the machine learning model. In this case, it will be a binary class, flood or not flood or dry. And another important concept is this partial order spatial dependency structure between locations based on their topographies. And we just defined it as the partial order weather between two locations, Si to Sj, as if water can flow from Si to Sj or not. In this small example, we have location Si in the lower left corner and Sj. And because the elevation of all the locations along the path from Si to Sj are higher than Sj, then we can say water can flow from here to there. And there's a dependency. And one note is that such topography information is considered, we only consider some simple effect. We do not consider the dynamics of the water, hydrodynamics. We do not consider the frictions, momentum, and other more complicated process. So you can imagine we just assume it's like a glass surface. And on the right is another simpler example, and this shows 8 consecutive locations. You can imagine these are 8 pixels along a line on a raster image, and the vertical axis shows the elevation values. So the intuition is that if location 5 is flooded, 2 to 4, 6 to 7 must be flooded as well. So this provides a dependency structure between locations based on topography. And next, this is the formal definition. We have raster framework and have some features like the spectral bands layers and elevation layer contain the topography. We also have some labeled pixels, whether the pixel is flat or not. It can be from other places outside the framework. And then we want to learn a machine learning model that can classify the pixels in the image into flat or dry. And we make several assumptions, and we allow the pixels to have noise and obstacles. And we assume the classes like flat or not follow some topography constraints. And so what are the challenges, specific challenges here? The first challenge is that the imagery may contain much noise and obstacles, especially during the flood disaster. It can be a cloud and there's shadows, and another major thing is the tree canopies in heavily vegetated areas obscure the view of whether there's a flood or not below it. And this area imagery also has varying illuminations. So even the same flood water surface may show different color. Another challenge is this topography constraints. And it shows this dependency structure that's anisotropic and partial order. And the data volume on the high resolution raster imagery is also large. We can easily have millions of billions of locations. So the challenges are interconnected. So we have this noisy data with obstacles in the features, and we need to also incorporate this topography structure, dependency structure in machine learning models that can overcome this noise and obstacles. And we also model this structure on a large data volume. So it really requires the idea to be efficient, computational efficient. And now let's take a quick view on the existing work. So I categorize these methods in machine learning as topography unaware methods and topography aware methods. The topography unaware methods include those that assume the IID distributions without any consideration of dependency structure. And some of these is considered a spatial autocorrelation effect within neighborhoods, like deep convolutional neural networks. And for these methods, they ignore the topography constraints and may produce implausible results and requires post-processing. And for topography aware methods, they try to use the elevation informations and terrains. And one way to solve is to use post-processing. For example, we can use global elevation values to compare. Generally, higher elevation tend to be dry, lower elevation tends to be flat. But this may not perfectly work well. Like in this example, sometimes this is not monotonic. And when we use global elevation, it may be wrong. And there may be more sophisticated methods in post-processing, like how to incorporate this terrain topography and to do some additional more sophisticated methods. But what I'm exploring here is to incorporate topography within machine learning models, try to capture the partial order richer terrains. And this is to complement existing methods, reduce the effort in post-processing. So before I introduce the details, I want to make a brief summary about the contributions in this work. My research is interdisciplinary. I try to make a balance to have both computer science contribution, novel methodology, and some domain applications and impact. So in computer science and machine learning AI perspective, we develop a topography-aware machine learning model called the hidden Markov tree, which I will introduce next, and develop some efficient learning algorithms. And later, we generalize the model using a deep neural network techniques and develop a co-training graph neural network-based co-training framework. And for the domain side, we apply the techniques tested in observation-based riverine flood inundation mapping and try to reduce topographically implausible result. And we collaborate with some federal agencies and try to deploy the tool for flood disaster response operations. This is still an ongoing process. So next, let's look at our idea. We'll start with this basic machine learning model called topography-aware hidden Markov tree. So the main idea is that we want to represent the spatial structure of the terrains and topographies using a graph or spatial graph. Especially there is a partial order dependency, so it will be a tree structure. And this is the example I showed earlier. If location 5 is flooded based on gravity, 2 to 4, 6 to 7 must be flooded as well. And such partial order can be represented in a tree structure on the right. In this tree, if any node is flat, then all the subtree nodes must be flat as well. And this is a reverse tree because it's not like a regular tree in computer science where each node have multiple children, but only one parent. Here, one node have multiple parents, but only one children. So we created this reverse tree structure and to incorporate the topography dependencies. And then we choose tree because it's simple and it can be efficient when we do the model learning and inference compared with a general graph or directly acyclic graph. And after we get a tree, we put it into a hidden class layer in a hidden Markov model. And about the tree structure, we explore different representations. We start with a simple tree, later borrow some ideas from computational geometry, like doing something called a contour tree, and with some computer science publications. Later, when we collaborate with domain experts, then we have more sophisticated terrain-aware tree structures. The main idea is that flat surface may not be flat, and it should be smoothly changing along a river. So we can have this heterogeneous a sequence of tree structures along the river to have one tree for small local regions or zones. But today, maybe I will only focus on the first simple tree structure to show the idea. Now let's look at how we build a machine learning model. So we use the tree structure to represent the topography dependency of whether the two locations will be flooded or not. And then we put this as a hidden class layer in a hidden Markov model. So it's called a hidden Markov tree. And it's generalized a common hidden Markov model from a sequence to a tree structure. And in this example, the grid nodes are the hidden class nodes. It's whether a location or pixel is flat or not. It's a class variable. And there's one location and it's also parent locations. And we know there's this partial order dependency. And each white node is the observed feature or spectral signature observed at the same pixel location with the green node. So we know in this model that when we classify a grid node or the class, whether it's flat or not of a pixel, we not only consider its own spectral signatures, but also this terrain topography dependency between other locations, whether they are flat or not in the tree structure. So that's the overall intuition. And we formulate this. This is a probabilistic graphical model. And because it has this tree structure, we can decompose the joint distribution of the feature nodes, class nodes into some local factors. And this really simplifies this distribution expression. That there's two type of terms. One is the feature conditional class. This is the first part. And then there's also the class transitional probabilities along the tree branches. And we further assume that the features are Gaussian, and there's a uniform class transitional probability between the class nodes. And one small thing that when we're modeling the transitional probability, it could be complicated because one node can have multiple parents and their combination of classes can be many. But fortunately, because we have the partial order constraints, we can simplify that. We don't need to permutate a large number of combinations. So we know because of partial order, if any parent is dry, then the current node must be dry. Otherwise, flood water will flow there. So then we can have this 2x2 transitional probability table. Like if any parent is 0 or dry, then the current node has a probability 1 being dry as well. And otherwise, we use a rho as a probability. And for the nodes that have no parent nodes, meaning they are mostly a local minimum area, then we use a prior probability to model the class class distribution. So this is the model formulation. And next, let's see the model parameter learning. One advantage of this model is that it's very transparent, and that's why some of the collaborators, they like this model, be able to know how it works. About the parameter learning, I will not go to too much details. So this model has several parameters. Some are related with the Gaussian distribution of the features in each class, and then a couple of parameters related with the class transitional probability. And the main challenge of the parameter learning is that we have both unknown class labels, the hidden variables, and the unknown parameters. So because of this, we use something called the expectation maximization algorithm, or EM algorithm, in machine learning. And this problem, the EM, is unique because it has this tree dependency structure instead of the IID distribution. So we need to consider this graph or tree structure. And the main idea of the EM algorithm is that we have both unknown hidden variables and unknown parameters. So we can initialize the parameters first, maybe through some random initialization, and then use it to infer the hidden variables, hidden class variables, and then marginalize out the hidden class variables using posterior expectation. Now it will be only the objective of likelihood is just a function of parameters. Then we can find the parameter that maximize the likelihood. But computing the posterior distribution is very challenging given the tree structure. And fortunately there's simple ideas using tree traversal that's very efficient. The process is something like this, passing messages along the graph or tree. And then after we get a parameter learned, then we can do class inference. And that can also be done through a tree traversal operations by propagating the message. So because the main operation is about the tree traversal, is very efficient. The time complexity is linear to the number of tree nodes. So because of this, even though we easily have tens of millions of pixel locations, we can still run the algorithm very fast. And now let's look at some evaluation results. And we evaluate in some test data set in Hurricane Matthew flood in 2016. This is a small study area we have seen. And we compare our methods with some existing methods. These are the results. So the last row basically shows the precision recall and F measure. For remote sensing people, this is the same as the user's accuracy, producer's accuracy, and then their harmonic means. And the last column shows the F-score average across all classes. And we can see our model performed really well on this tested data set, and even better than the current state-of-the-art deep convolutional neural network called the UNet model. And also for that deep learning model, we use more training data because it cannot be trained for a few pixels. It has to have the contiguous patches being labeled wall to wall. And this is even more training data compared with our hidden Markov tree model. And here are some visualizations. This is the area imagery and elevation terrain information. And this is the random forest result. It has the IID assumption, and then some other gradient boosted model. And the middle one is the deep learning result. It does identify a lot of the flood areas, but it also has mistakes, especially for the areas covered by tree canopies. Based on the spectral signature, it really cannot distinguish whether the tree canopies are in flat or dry areas. Like this area highlighted in the white circle, it is dry, but it's still predicted as flat. It is topographically implausible result. In the right is our result. So this is our original idea, and this is some evaluation about the computational scalability. Like this is on small simulation data set, and we see that on around 20 million simulated pixels, the model can process in less than 3 minutes. And next, I want to show our extension of the model. We leverage this disciplinary knowledge of the terrain topography, but make it more general using deep learning framework. And the main motivation is that our earlier hidden Markov tree, it makes several rigid assumptions, like the features are Gaussian, but in the spatial remote sensing, the context is very important. And also in the transitional probability, we assume the uniform transition probability matrix for every node. But how can we generalize these assumptions? Because if we have these assumptions, we have to carefully select the training samples of pixels to make sure they are representative for the test image. And so that the iteration process of the EM algorithm in model learning will converge to the right state. But can we make it more rigorous or robust? Like learn the spatial contextual features, like using the convolutional neural network, and then learn the class transitional probability at every node. But for the first one, this is what deep convolutional neural network do. The second one, this is about a graph neural network. And I will explain next why these are for these challenges. So some reviews about graph neural network. The first about traditional or more common deep convolutional neural networks is, so here's a raster image with or rasterized spatial data, and every pixel has a feature. And the way it works is to use a window with parameters. And when it's scanned at any location, it will do a convolution operation, which is doing a linear weighted sum, and then apply a nonlinear activation of this gray location, produce the output for the next step. So this is a common convolution. And what a graph neural network or graph convolutional model is trying to do something similar, but on the node features on the graph. And this is non-trivial because the graph is different from the raster. It does not have this regular structure. There's no fixed neighborhood. So we cannot directly apply this convolutional window from image to graph. And to address this issue, some people come up with ideas, and it's not too complicated. Just first to aggregate the neighbors' features like this, and then apply a same like a neural networks on every nodes based on their aggregated features. This is essentially what current graph neural network does. Why this is useful for our traditional probability modeling? So if you go back to this hidden Markov tree example, it's really captured the current node, like node 5, whether it's flat or not. Conditions on the condition the condition on the parent node classes. So whether node 7 and 2 are flatted or not. So this is similar. Such conditional probability is similar to the graph convolution operations. So assume we can initialize every node location with the initial class information. Through graph convolution, the neighbor's class information will be aggregated and be used to produce the output for the current node final class prediction. So the current node's node 5's class prediction is really based on the neighbor's classes, and that's reflect this traditional probability. So we can use the directed graph convolution to learn class traditional probability. So now we see that actually there are two representations. One is we can use a regular grid image to learn the spectral, the contextual features in the image. We can use the graph representation to incorporate these topographic constraints. Because of this, we develop this co-training framework. I will not go to the mathematics part, just focus on the intuition. So we have dual representations. For the image representation, we use a convolutional neural network. So from an input image, we can have very small number of labeled image patches. And we use that to train a CNN or convolutional neural network model, and then predict some initial probabilities. This may not be very good because there are limited number of training labels. But then we also have this graph representation for the same number of locations, and feed into the initial predicted probability from the left. Through the graph convolution, the result will be more topographically aware, a more topography consistent result. So from the convolution, we can feed into graph convolution, incorporate the topography constraints, and then feed back into the CNN models to train a better predicted probability. And this process iterates until the two models converge. And we actually have a theoretical framework to formulate this as using variational EM. And this is a semi-supervised learning algorithm. It can work for a limited number of training labels. And next, let's take a look at the results. So we are using the similar type of imagery, but with a different number of labeled image patches. Each image patch is actually around 224 by 224 pixels. And we change the number of labeled patches from 5 to 400. We can see the different models have different performance. If we just directly using the deep learning deep convolutional neural network, it does not perform well when the number of labeled patches is small. If we add some existing methods to mitigate these limited training labels, like a self-training, or even use this tree structure as a post-processing using conditional random field, it does improve things quite a lot, but still not perform very perfectly. But our methods using the graph co-training in the red curve still show a good accuracy, even though there are very few labeled patches. So this is some visualizations. This is a very small test area, and this is ground truth. And the next one is a deep neural network, UNet prediction, with quite a lot of errors. And using self-training and post-processing, it does improve, but still quite some errors there. But in the contrast, the right is our result. It's closer to the ground truth. So far, I have showed the idea, and next I see a more realistic real-world example. This is collaborating with agencies, and basically we use a more realistic tree structure from the terrain analysis, And this tree is from our collaborator. So we have this sequence of hidden markup trees along the river. And this is some preliminary results in a Midwest flood in Omaha, Nebraska, 2019. On the left is the world view imagery. On the right is deep learning result, like something like an autoencoder UNet model. We can see identify most of the flood water actually, but still it's not very smooth. Like areas highlighted by the white circle is below tree canopies. And the next, this is the result after you apply this hidden markup tree on top of it. We can see it produce more consistent result. But this is still a very challenging problem. We are still working on this. So next, let me quickly discuss some potential future directions. And the first area we are working on now is to develop GeoAI separated structures that can serve different scientific domains, like geoscience domains. And in this example, we have a new NSF Office of Infrastructure grant, try to develop a distributed machine learning system for these hydrological applications. And it's in collaboration with my colleague at the University of Alabama, Birmingham. And I'm also, another thing I'm interested in, very interesting, is to explore physics-guided AI models for scientific application, especially for geoscience applications. And one example in the coastal domain is like the coastal flood. I have explored the riverine flood, and the coastal flood is more complicated. It has more complicated physical process, involves numerical models, and there's a lot of spatial temporal variables in it. So I'm also curious about, eager to explore how AI models and simulation models can help each other, like maybe produce more observation-based data product that feed into numerical model as input, or maybe it's a two-way street. The physical model should also be used when we design AI model to make it physics aware, so that the results are more trustworthy. And how to integrate this neural network with the differential equations commonly used in many simulation models. And this is not only for the coastal flood models. In climate models or other models, geodomain models, there's common challenges. So I'm interested to learn and collaborate with the domain expert in this field to explore any potential ideas. Another topic I'm interested in is to develop this GeoAI technology to analyze citizen science data, like volunteer geographic information. And this is motivated by the limited or paucity of ground truth in a lot of geo problems. So we have the physical like field or ground sensor, but those sensors sometimes is limited. So if we have this large scale, near real time, low cost, this citizen science data from quote unquote social sensor, it can somehow provide weak labels, and this can be used for AI training algorithms. Like example shown here, there are both VGI with an explicit mapping purpose called explicit VGI, although may not have a mapping purpose in mind, but it really shows what happens in the location around the publisher. And along this line, I'm interested to explore how to develop a weak supervised learning that can address the data quality challenges, like a weak noisy label semantics. And one idea is to use the domain constraints to do the data augmentation. And sometimes the label may have the vector annotation uncertainty or registration errors, and how to refine this while training the deep neural networks. And also sometimes this social media may not be geotagged. Very often it's not. How can we identify the location names embedded in the text so that we can map these labels and context into other layers? And for that one, it may involve natural language processing. So this is another supported by ongoing NSF grant. in machine learning data science track. So this is my current work. The long-term vision is to explore different applications, and there's a lot of technical challenges like multimodal data and robustness to outliers, and how to incorporate the physics awareness into AI models, and then how to address large data volume for scalability and efficiency. And for interdisciplinary research, I'm always interested to learn from our collaborators in scientific domain like geoscience, geography, and to work in an interdisciplinary team together. And this is acknowledgement of my collaborators from federal agencies and my students. And next, I would like to call for questions or suggestions. Thank you.
Thank you very much, Dr. Jiang. And we can either entertain questions on chat from people in the group or anyone in the classroom. We do have one question from someone in the classroom.
Dr. Jiang, thank you very much for your nice presentation. I want to know, is there any current model that is working on to track the sea level rise or its impact in coastal areas?
Sorry, could someone phrase the question again? Yeah.
The question is there a current model to track sea level rise in the coastal area?
Yeah, that's a great question. I'm just started learning about this domain, about sea level or coastal challenges. I'm not an expert in this, but I do know there's a physical model certainly there. And about the AI model, I think it's still an open challenge about how to incorporate this physics-based simulation model for ocean waters, water levels, how to incorporate this into AI. I think this is still not well solved yet. Yeah.
Okay. Are there other questions?
I have a question.
Yeah.
Hi, Dr. Jiang. Thanks for your presentation today. I'm currently taking your course on deep learning for spatial temporal data, and I already recommended to some of my colleagues. And my question is also related to coastal sciences, but what I was thinking was, when working with no-imagery spatial temporal data, could you apply a similar approach with the hidden Markov tree and convolutional neural networks, as you did for imagery classification, also considering topography and spatial autocorrelation? Do you know what would be different? What should you consider?
Yeah, thank you for the question. So that's based on what data set and application problem you are looking at. Could you just elaborate more about what data set or what kind of problem you are trying to solve on the imagery?
With no imagery data, I'm thinking about tide gauge and buoy data for coastal flooding.
Yeah, that's a great question. I'm not sure about the coastal flood because the hidden Markov tree model I developed is terrain-based, and it's largely maybe more useful for the river flood. For the coastal, I think it's a different physical process. I'm still learning about it. It's about ocean currents and other things. So the hidden Markov tree may not be directly applicable. But I do agree with you that this kind of structure can be also useful when there's no spectral features from the imagery. But if we have the ground sensor observations, like from river gauges, then that can also be very useful. And it could be used because we can generalize the model to remove some of the observed feature nodes. And then the same framework can be used to infer the hidden class nodes. And we have some work on that actually, but more for river flood, when we assume maybe there's very limited area being observed, either by ground sensor or area UAV, something like that. Then how we infer more complete spatial extent. Yeah, that's a great question.
Okay, good. Thank you. I'm gonna reach out to you later today.
Yeah, let's talk.
Okay, I have one question.
Yeah.
Have you compared your results with a relative elevation model or the planar bathtub model, where you have a few sites and then, you know, assume a downstream slope and just to see how different that would be?
Yeah, that is a great suggestion. I have now explored these related work. I think it will be interesting to see how the result looks like in some comparison. If you have any like a reference for these papers, I'd like to read and to see. Yeah, I haven't compared those for now yet.
Okay, yeah, I do. We can talk later.
Yeah.
I know you have a class coming up, and technically it's the end of our period. So we do appreciate your time and hope that you get to network and communicate with us more in the future. Thank you for.
Yeah, thank you for the invitation. I'm really glad to be here, and I'm really interested in collaborating with faculty or researchers at a geography department. Please let me know if there's any ideas for collaboration. Reach out to me. Thank you.
Sure. Bye-bye.
Yeah, bye.